Atomic radius is going to be the topic in this lesson, and this is the first lesson in a whole chapter on the periodic trends of the elements. We'll do atomic radius in this lesson, we'll do ionization energy in the second lesson, and then we'll do electron affinity in the third lesson. Now, we'll start off this lesson talking about atomic radius, and to explain part of that trend, because a little bit of it's going to be a little counterintuitive, we'll talk about what's known as effective nuclear charge. We'll then move on to seeing how the atomic radius directly affects bond lengths. We'll move on to talking about ionic radii. So an atomic radius implies neutral atoms, whereas ionic radii are going to be the radii for both cations and anions. And then finally, we'll polish this lesson off looking at comparing the radii of what's known as an isoelectronic series, a series of atoms or ions that have the same electron configuration. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. So let's dive into this. So first thing we got to realize is that when we're talking about the atomic radius, we're talking about the size of the electron cloud, not the nucleus. Now, we'll see a little bit of a variance here with the mass, because most of the mass of an atom is in that nucleus. That's where the protons and neutrons, which comprise most of the mass of an atom, are. So, but the electrons, which weigh very little, are what really are going to determine the radius. And a lot of times we'll be looking at the outermost shell of electrons, the valence shell, specifically determine that outermost boundary of an atom. Now, this is a time where if you were sitting here with me, I'd ask you if you'd ever been to France, if anybody had ever been to France, and I'd usually get a few hands, and I'd say, what do you remember about France? And a lot of people will say, the Eiffel Tower and stuff like this. But inevitably, some people are going to start talking about the wine and the food and, the cheese and the eclairs and things of this sort. And if you spend too much time in France, you are going to get fat. And it turns out just like francium. So it turns out francium is the fattest element on the periodic table. And so the general trend for atomic radius is that atoms are going to get larger as they go down a group, but they're also going to get larger going right to left. And this is going to seem a little bit counterintuitive at first. So, and the reason, because masses actually get larger generally going left to right. So why is the atomic radius getting larger going right to left? Well, it's going to come down to what's known as the effective nuclear charge. And we're going to have to, kind of parse this out a little bit, and we'll use 3 examples to kind of figure this out. Okay, so we're going to take a little closer look at the horizontal trend on the periodic table. And to do this, we're going to compare sodium to magnesium to aluminum. Now, again, on the periodic table, we can see that as we go from right to left, we should get larger. So sodium should have the largest atomic radius, then magnesium, then aluminum. And indeed, if we look at some published values, sodium at 190 picometers is larger than magnesium at 145 picometers, is larger than aluminum at 118 picometers. And picometers is kind of a common unit here for atomic radii, but not the only one you could see. Now, nanometers not so common because you're going to get decimal numbers. Like this could be 0.19 nanometers, 0.145 nanometers, and 0.118 nanometers. But another common unit you might get are angstroms. And so whereas a nanometer is 10 to the negative 9 meters, an angstrom is 10 to the negative 10 meters. And so instead of moving back 3 decimal places to go from picometers to nanometers, we just move back 2 decimal places to get to angstroms. So this would be 1.9 angstroms, 1.45 angstroms, 1.18 angstroms. So another common unit out there. But regardless of unit here, we can see that sodium's definitely larger than magnesium and magnesium's larger than aluminum, just as we said according to general trend. It increases going from right to left on the periodic table. Now, again, this is counterintuitive because aluminum is actually the heaviest out of these 3, and sodium is the lightest. So, but again, it's not about how heavy or light your nucleus is, it's about the size of your electron cloud. Now, we'll see why this is. It comes down to something we call effective nuclear charge. So, we'll talk about nuclear charge first. So sodium is atomic number, if you look at atomic number 11 on the periodic table, and so that means the nucleus is going to have 11 protons and have a plus 11 charge. Whereas magnesium is atomic number 12, and its nucleus will have a plus 12 charge. And then the aluminum's atomic number 13 will have a plus 13 charge due to the 13 protons in its nucleus. And so we get a more and more positively charged nucleus as we go across a period. And then we're going to take a look at the electrons here. And so I've kind of broken this up and using kind of the Bohr model of the atom here. It has some utility in this case, even though we know it's a little bit wrong, but it has some utility in explaining this effective nuclear charge. Now, in the first shell of electrons, all of these have 2 electrons, and I forgot aluminum's electron configuration here. Let's get it up on the board. All right, so all of them have 2 electrons in that first shell, and so I'll draw those in. All right, then they all also have 8 electrons in that second shell, so 2s2, 2p6, 2s2, 2p6, 2s2, 2p6. That's 8 electrons in the second shell. And then finally, what we're going to see a difference is in the valence shell, the outermost shell. With sodium, we're just going to have 1 electron out there. So for magnesium, we're going to have 2 electrons out there. So, and then for aluminum, we're going to have 3 electrons in that valence shell. Okay, so way this works, the outermost electron determines the outermost boundary of the atom and therefore the radius. And the question is, how attracted is that electron to the nucleus? The more attracted it is, the closer it's going to be on average, and the smaller the atom. The less attracted it is, then the further it's going to be away, and the larger the atom. And so the way this works, this electron, even though it's attracted to the 11 protons in the nucleus, it's also repelled by all these electrons that are closer to the nucleus than it. And so we have this lovely rough approximation for calculating the effective nuclear charge that just says, so Z here stands for charge, and so the effective nuclear charge is equal to Z, which is the nuclear charge, which in sodium's case would be 11. And then minus what's known as the shielding or screening electrons. They're electrons that are closer to the nucleus than the ones you're talking about. So in this case, if we're talking about the valence electron, well, that means all the core electrons would be considered shielding electrons, which in this case is going to be 10 of them. And so in the case of sodium, 11 minus 10 is going to get us an effective nuclear charge of +1. And again, the greater this effective nuclear charge, the more attracted to that valence electron is to the nucleus, and the smaller it's going to be. Now, if we move on to magnesium here, now there's 2 electrons in the outermost shell. And the idea here is that, in this case, when they're both in an s orbital as they are, they're actually going to spend most of the time on opposite sides of it. And so they're equidistant away from the nucleus, and so they're really not going to shield each other away from that nucleus. They're not going to screen each other from that nucleus. And so they're not going to contribute towards each other in this screening one. And that's the idea, is that all the valence electrons aren't going to contribute anything too significant here. Now, the truth is they actually do contribute a little bit, but we're just got a rough approximation for equation here. So in the case of magnesium, then, these 2 electrons out here now feel a +12 charge from the nucleus, but there's still only 10 core electrons, and so the number of screening electrons is still only 10. And so now your effective nuclear charge is 12 minus 10, and that's going to be +2. And with a higher effective nuclear charge than for sodium, that means that these outermost electrons have a greater overall attraction to the nucleus and are going to get pulled in tighter. And one, I've drawn it smaller, but also again, we see that 145 picometers is indeed smaller than 190 picometers. And so as atomic radius is increasing to the right, what we're going to find out is that effective nuclear charge is increasing, atomic radius is increasing to the left. It's because effective nuclear charge here is increasing to the right in the opposite direction. Okay, so moving on to aluminum here. And so aluminum now has 13 protons in the nucleus. So our Z value is 13. But again, the electrons in the valence shell are all roughly equidistant away from the nucleus. And so we say to a rough approximation, they don't really contribute to this shielding value. They're not shielding each other from the nucleus. Only the core electrons are doing this. Now, again, this is not 100% true, but to a rough approximation, it'll establish the trend for us here in atomic radius that we need. And so in this case, we're still only going to subtract off the 10 core electrons and get an effective nuclear charge of +3. And again, these are just rough approximations that effective nuclear charge. They actually have more complicated equations that can give you a much more exact value and stuff like that we're not going to go through, called Slater's rules and stuff like this. We're just going to go through this rough approximation and call it good. It'll establish the trend that we need. So what we see here, aluminum has an even higher effective nuclear charge. Therefore, the outermost electrons are even more attracted to the nucleus. They're pulled in even tighter, and therefore it's even smaller here at 118 picometers. And what's nice here, it turns out if you want to look at the effective nuclear charge on the valence electrons, it turns out it ends up being just simply equal to the number of valence electrons. So in this case, the group 1 metals all have an effective nuclear charge on the valence electrons of +1. The group 2 metals of +2. Aluminum here in his column +3, carbon's column or group +4, nitrogen's group +5, the chalcogens and oxygens column +6, the halogens +7, and the noble gases +8. And so because the effective nuclear charge is increasing as we go left to right, they're getting smaller and smaller and smaller as they're more attracted to the nucleus. And that's why the atomic radius is actually increasing in the opposite direction. Cool, so a couple things you should realize here is one, that again, as you go down a group, the size gets larger, not because there's any difference in effective nuclear charge. There's not. They were all +1, right, in the group 1 metals. So, but again, you're just getting more and more shells of electrons, and that's why it's getting bigger. So it's the horizontal trend here. Again, they're getting bigger going to the left because the effective nuclear charge is getting bigger going to the right. Or you could say that the atomic radius goes up as the effective nuclear charge goes down in the opposite direction, or in the same direction, I guess. Cool, so that's kind of how this works. We use it to explain that effective nuclear charge. So if I asked you, who's bigger, cesium or rubidium, you should hopefully say cesium is larger, has a larger atomic radius. Now the question is why? And if I said the answer is because it's got a larger effective nuclear charge, well, that wouldn't be true. The effective nuclear charge on the valence electrons for both of these is +1. So that wouldn't be a correct statement. Again, cesium is bigger, but not because of effective nuclear charge. It's bigger because it has more shells of electrons. Now, if instead I say I have you compare cesium and barium, well, again, who's bigger? Well, again, the general trend is francium's the fattest. So going to the left, cesium would be larger than barium. Now the question would be why? And in this case, it would come down to effective nuclear charge. Cesium is larger because it has a lower effective nuclear charge, or you could say cesium is larger because barium has a higher effective nuclear charge. You could say, phrase that either way. But again, it's this horizontal trend that we explain by this idea of effective nuclear charge. And so as you notice, as we move across a period from left to right, like we did from sodium to magnesium to aluminum here, your Z value is increasing by 1. You get 1 more proton in the nucleus, whereas your shielding value stays constant all the way across that group. And that's why we can go from +1 to +2 to +3, +4, +5, +6, +7, and then +8 when you actually reach the noble gases. Now, again, this is a very, very rough approximation. If you actually looked at actual values, the noble gases are closer to like an actual value of like +3 or +4. So, but again, to a rough approximation, that's all we're going for here because we can totally explain the trend away now in terms of this effective nuclear charge. So now it turns out that we can look at bond lengths, and it turns out that bond lengths are really just the sum of the two radii of the two atoms here. So notice bond length is defined as the distance between nucleus to nucleus. And so we've got the radius of one atom there, and then the radius of the other atom there. And it's simply the bond length is really just the sum of those two atomic radii. It turns out for a covalent bond, which we'll study in more detail in the next chapter. But it turns out we have ionic radii that you could use if it's really more of an ionic bond. And so it turns out we have both atomic and ionic radii, but it turns out their values aren't going to be super, super different. So, but if you know, especially after next chapter, if you've got ionic bonding versus covalent bonding, with covalent bonding, you want to use those atomic radii. With ionic bonding, you want to use the ionic radii instead. So if you've got two non-metals, go with the atomic radii, that's a covalent bond. But if you've got a metal with a non-metal, it'll be a little more accurate to use the ionic radii because you're forming an ionic bond in that case. Cool, but ultimately, you might get a question that just asks you to compare bond lengths, and ultimately, larger atoms make longer bonds. And so, oftentimes, they'll give you an example where you do like carbon fluorine, carbon chlorine, carbon bromine, carbon iodine, where they keep one of the atoms the same all the way across. That way, the only difference is therefore the radius of the other atom. And so if I said, which of these is the longest bond, you'd pick the carbon iodine bond. Again, they all have carbon in common, but fluorine is smaller than chlorine, chlorine is smaller than bromine, and bromine is smaller than iodine. And since iodine is the largest of the other four atoms, it's therefore that carbon iodine bond is going to be the largest, or the longest in this case. Now I could add one other thing on here. Maybe I do something like add a fifth choice on there where I do silicon to iodine. Now of the other four here, we obviously said that carbon iodine was the longest. But now if I said out of these five, which one's the longest? Well, out of the top four, you can already rule out the first three, right? Carbon iodine's the longest out of those four. But then if you compare it to the silicon iodine, now they both have iodine in common, but silicon is larger than carbon. And so the silicon iodine bond would now be the longest if we add that extra answer choice there. So again, a lot of times you'll see just something like this where you have one atom in common, but even if you don't have one atom in common, usually you'll be able to compare several of them at a time, or at least a few of them at a time, and rule out some. And they might ask you for the longest bond. They might also ask you for the shortest bond. So now we're going to talk about ionic radii. And again, atomic radii assumes you have neutral atoms. Whereas when we talk about ionic radii, now we can talk about cations and anions. Cations, again, being positive ions and anions being negatively charged ions. And the big thing you should realize here is that when you go from a neutral atom to a cation, you're going to lose at least one electron. So like in the case of potassium, to go to a potassium ion, we're going to lose one electron. And notice that's the most common ion that potassium is going to form, being a group 1 metal. Most common ion it forms is +1. Calcium, on the other hand, being a group 2 metal, most common ion he is going to form is going to be +2. But in either case, either potassium or calcium, we're going to lose electrons to turn into the cation. And what you should realize, though, is that if you lose electrons from your electron cloud, then it should make intuitive sense that your electron cloud gets smaller. And the idea is that, the more electrons you have around this nucleus, they're all attracted to the nucleus, but they're all repelled from each other. And the more of them that they are, they want to get close to that nucleus, but they're also wanting to stay far apart from each other. And so the more electrons you have in your electron cloud, the larger it's going to be just due to their repulsions and stuff like this. And so as you go from potassium to, say, potassium +1, what you're going to find is that it's going to get considerably smaller. And it turns out it's not just a little smaller. If you look on your handout there, we got, potassium here is at 243 picometers, whereas potassium +1 here is at 133 picometers. That is a significant reduction in size. It's not just like it's a little smaller, it is significantly smaller. And one thing you should realize too is that when potassium loses that one electron, it's actually losing the entire valence shell. Another reason why you might realize it's a very significant reduction in size. Now, on the other hand here, we do the same thing for calcium. And again, calcium here loses 2 electrons to become calcium 2+, and you lose 2 electrons, you're probably going to even have a more significant reduction in size, losing 2 electrons instead of just losing 1. And here we go from 194 picometers to 99 picometers, which essentially is almost being cut in half in terms of size. But one thing we should realize is that cations, their ionic radii are smaller than their atomic radii. Whereas anions are going to be the exact opposite. When we go from a neutral atom to its corresponding anion, so we actually are going to gain electrons. And if you gain more negatively charged electrons in your electron cloud, they're going to repel each other and spread out a little bit and get larger. And so in the case of sulfur here, sulfur 2- is significantly larger, the sulfide ion. And same thing with chlorine here. Even gaining just 1 electron, it turns out it gets significantly larger. And we have to be able to explain this. So because this one, it doesn't seem to make quite as intuitive sense. You're like, well, Chad, we're just adding, electrons to the same valence shell. We're not actually going to a new valence shell or anything like that. And we said, as long as you're in the same valence, they don't really shield each other all that much. Well, again, we said it's, for a rough approximation, when we calculated effective nuclear charge, that's what we use. But the truth is they do shield each other some, more than we, rounded to 0 before, but they do shield each other. And so when we add electrons to that electron cloud, it does lead to actually a significant increase in size here. So in the case of sulfur, we got, 88 picometers compared to the sulfide ion at 184 picometers, more than doubling in size. And same thing with chlorine here, at 79 picometers going up to 181 picometers, again, more than a doubling in size. It actually turns out to be rather significant. But the big thing you should realize here is that anions have an ionic radius that is considerably larger than the corresponding atomic radius, where once again, to contrast that with cations, the ionic radius was smaller than the atomic radius. So you might get a question on the test that says something effective like, which of the following has an ionic radius that is smaller than the atomic radius? And so you should first realize, okay, if the ionic radius is smaller than the atomic radius, that's a cation. Because had the ionic radius been larger, that would have been an anion. Okay, so the question then is, what kind of elements form cations? And so it's, not so clear, but what you should realize is that you've already learned that it's metals that form cations, or it's typically the nonmetals that form anions. And so if you get a question that says, which of the following has an ionic radius that is smaller than its atomic radius, you should realize they're talking about something that forms cations, and they're talking, therefore, about a metal. And so out of your answer choices, there's probably one metal and a bunch of nonmetals. But they could ask that in reverse too, right? They could say, which of the following has an ionic radius that is larger than its corresponding atomic radius? And if your ionic radius is larger than your atomic radius, you're an anion, and it's a nonmetal that's going to form an anion. And again, your answer choices, you probably have one nonmetal, and then the rest are metals. So they could ask it, a little bit of a tricky way there, but now you're prepped for that tricky way. And that's ionic radii. Now, one other place you might be comparing ionic radii is if you're comparing things of the same charge. Now, notice we now know how to compare an ionic radius to its corresponding neutral atom. But comparing a bunch of different ions to each other is not so easy. Now, we've got the trend for comparing a bunch of neutral atoms. Again, francium was the fattest, but again, that's assuming you have all neutral atoms. If you've got a bunch of different ions with different charges and stuff like that, there's only a couple different ways we can actually have you compare different ionic radii, as we'll see here. Okay, so one place we might actually have you compare ionic radii is if you're just comparing a bunch of ions that have exactly the same charge. And if they have exactly the same charge, in this case, they're all +2. Which means their ionic radii are all considerably smaller than their atomic radii, but probably by the same degree with being all +2. And in such a case, you can probably just use the atomic radius trend to compare these ionic radii. And so in this case, if we just compared magnesium to calcium to strontium to barium, and I said, which is the largest, we'd look at the periodic table to be like, well, magnesium is the smallest, and it increases going to barium as the largest. Well, that was if they're neutral atoms. But even if they're all +2, well, they're all smaller than their corresponding neutral atoms, but barium 2+ is still going to be the largest out of the four if they all have the same charge. However, what if we did this? And made 3 of them have a +2 charge, but 1 of them didn't. And we might be like, well, shoot, if they were all +2, we'd know barium was the largest. However, strontium here without the +2 charge is considerably bigger than actual strontium 2+. Now, if it was strontium 2+, I know barium 2+ is bigger, but because it's just plain old strontium, which one's going to be bigger? Well, the truth is it's probably going to be strontium. Again, when something becomes a cation, there's a significant reduction in size. So now, even though I say strontium probably is the largest, this is probably not a fair comparison for most of you. It's probably not something they're going to ask you. And so if you're going to be asked a question on comparing ionic radii, you're almost undoubtedly going to be asked to compare things of the same charge, or we'll see one other case here in just a second. Okay, so the one comparison you might make where you're comparing a bunch of ions and atoms potentially with different charges is if we have what's called an isoelectronic series here. And iso means the same. And so we talked about what an isoelectronic series was very briefly in the last chapter, but an isoelectronic series is a series of atoms or ions that all have the same electron configuration. In this case, they're going to have the same number of electrons and the same electron configuration. And so if we take a look here, so argon here has 18 electrons, whereas sulfur normally has 16, but sulfur 2- is going to have 18 and look just like argon in terms of the electron cloud. So Cl-, again, chlorine has 17 electrons, but Cl- is going to have 18 as well, and both of these are isoelectronic with argon here. So potassium +1, so go over here, potassium's got 19. Neutral potassium's got 19 electrons, but potassium +1 is going to have 18, just like argon. And then finally, same thing for calcium here. And calcium's atomic number 20, but it has 20 electrons, but calcium 2+, once again, is going to have 18 electrons. And so in an isoelectronic series, they're all going to have the same number of electrons, in this case, all 18, and they're all going to have the same electron configuration, in this case, as argon. So 1s2, 2s2, 2p6, 3s2, 3p6, all of them. And so the difference isn't in the electron cloud. What the difference is going to be is how many protons are in the nucleus. And so if we look at the nuclear charge here, which is the atomic number, so here for sulfur, the nuclear charge, not the effective nuclear charge, but just the nuclear charge is +16, the same as the atomic number. Here for chlorine, it's +17. For argon, +18. For potassium, +19. And for calcium, +20. And so we see here that calcium's nucleus has the most positive charge. And so the question is, whose nucleus is going to be attracting those 18 electrons? Again, they all have 18 electrons. Whose nucleus is going to be attracting those 18 electrons in the most? Well, that's calcium, because it has the most positively charged nucleus, because it has the most protons in its nucleus. And therefore, as a result, calcium 2 plus is going to be the smallest in the series. So, and then potassium, and then argon, and then the Cl minus, and then S2 minus is going to be the largest in the series, having the lowest nuclear charge. So these, the 18 electrons in sulfur here are going to experience the least attraction and therefore be the farthest from the nucleus and have the largest radius in this case. And so when you have an isoelectronic series like this, the most negative one ends up being the largest and the most positive one ends up being the smallest. And it just comes down not to effective nuclear charge, but just to plain old nuclear charge. Now don't forget everything you've learned in this lesson, because we're going to use part of this atomic radius trend to explain some things when we talk about ionization energy in the next lesson. Now, if you found this lesson helpful, would you consider hitting that thumbs up button? Best thing you can do to make sure YouTube shares this lesson with other students as well. And if you're looking for a bunch of general chemistry practice, check out my general chemistry master course. It's full of quizzes and chapter tests, practice final exams, and final exam rapid reviews if you're prepping for finals. Free trial is available. I'll leave a link in the description. Happy studying.